Hi, welcome to the video on Faraday's laws of electromagnetic induction. Today we are going to study on first law, second law and Lenz's law also under this video. So Faraday's laws of electromagnetic induction, the first law states that whenever a flux linking a coil, okay, or a circuit changes, an EMF is induced in the circuit. Or in other way, we can say whenever the flux linking a coil or circuit changes, an EMF is induced in the circuit. That is Faraday's laws of electromagnetic induction, first law. The second law states that the magnitude of the induced EMF is equal to the rate of change of flux linkages. That means amount of flux linking the coil. So the direction of the induced EMF was given by Heinrich Friedrich Emil Lenz. So the Lenz's law will give you the direction of the induced EMF. So before that, the second law, we can write the mathematical equation. So the magnitude of the induced EMF. So we can say magnitude of the induced EMF I have represented here. E is equal to minus n into d phi by dt. So negative sign is because of the Lenz's law, because it indicates the direction of the induced EMF. So we say whatever the amount of flux linking the coil, the magnitude depends on the amount of flux linking the coil, and the direction of the induced EMF is such that it opposes the cause producing it. See, as I said, if you take a solenoid, okay, just let me write a solenoid here, and you are passing a voltage, okay, or let me say this is a AC voltage. So whenever the current is flowing here, the flux is produced, and that flux is linking this coil. So that flux is linking this coil, I said EMF is induced according to second law, and the magnitude also is depending on the rate of change of flux. So but Lenz's law states that whatever the induced EMF produced will be opposing the cause producing it. If you look at it, the voltage will give you the current, and current will flowing in the coil will produce a flux, and this flux will produce, linking the coil, will produce the EMF induced. So this EMF induced will be in the direction in such a way it will be opposing the cause producing it. So the cause for producing this EMF is this voltage. So we can write it is opposing. The word opposes here indicates the negative sign. So the cause opposing it, that is it opposes the supply voltage. We can say, it opposes the supply voltage. Okay, so E indicates the EMF induced in volts, where N is the number of turns, because the number of flux linking the coil depends on the number of turns, as I said in the laws of magnetism, correct? So this turns increases, and the number of flux linkage also increases, EMF is induced. That is one way. And if you increase the current, the flux produced will be increased, and that maximum amount of increased flux will be linking the coil, so EMF can be induced. So the rate of change of flux linkage with respect to time is given as d phi by dt. So with this, we can now understand what are the laws of Faraday's laws of electromagnetic induction, first law, second law, and Lenz's law. So next, for this, I can give a better example here. Suppose a coil has n turns. Okay, let me say, as I said, the solenoid has n turns. Okay, 3, 4, 5, it goes. So it has n turns, and the flux passing through it changes from the initial value of phi 2 when it changes in t seconds. So it changes from phi 1 to phi 2 in t seconds. Let us understood that. So initial flux linkage will be with respect to phi 1, and in final flux linkage, maximum linkage with respect to phi 2. So n phi 1 will be the initial flux linkage, and n phi 2 will be the final flux linkage. So rate of change of flux, as I said, d phi by dt. So d phi by dt means this is the change of flux I'm talking. So this is n phi 2 minus n phi 1 divided by t. So therefore, this I'm saying this is proportional. Okay, sorry, we can say rate of change of flux linkage is that, but E is proportional to d phi by dt. That is, the EMF induced is proportional to d phi by dt. So we can write here. So I can write here now. I can write now E is proportional to n phi 2 minus n phi 1 divided by t. So to remove this proportionality, I will use a constant E is equal to k into n. Okay, number of turns is same. So phi 2 minus phi 1 by t. Correct. So k, if I put the k as 1 in this equation, okay, then this equation becomes n into phi 2 minus phi 1 divided by t. Correct. So we can write the flux linkage phi 2 minus phi 1 as the differential in flux linkage. Therefore, E can be written as, what we can write this equation now. E is equal to minus n, because of the Lenz's law, as I said, it opposes the cause producing it, minus n into d phi by dt. This is how you get the equation for the EMF induced. In the next slide, you can come up with the Fleming's left and right hand rule. So in the left hand rule, if you observe, okay, this you have studied in the grade 12. So in the left hand rule, what it says, in the left hand rule, if you look at that, when a current carrying conductor is placed in a magnetic field, it experiences a force which acts in a direction perpendicular both to the direction of the current and the field. So the magnitude of this force is given by, you can say F is equal to, I can write the magnitude of this force is given by F is equal to F is equal to BIL. Okay. So here B, as we know, we have defined this as a flux density of the magnetic field. I is the current carrying by the conductor in ampere, and L is the length of the conductor. So the force, when a current carrying conductor is placed in a magnetic field, it experiences a force. That force is given by F is equal to BIL, and it is given by Fleming's left hand rule. So now coming to the right hand side, we have Fleming's right hand rule. So in this right hand rule, it is used to find the direction of the induced EMF and current in a coil. So this is specially applicable where the conductor moves at right angles to the magnetic field. So here the four fingers, okay, the three fingers has been stretched here. That is the thumb, forefinger and middle finger are at right angles. Exactly, when you stretch at right angles, the forefinger points in the direction of the magnetic field, the thumb in the direction of the motion of the conductor, then the middle finger points in the direction of the induced EMF. So this is how we need to understand the direction, motion and the field of a given magnetic field. So in the next chapter, we are going to discuss dynamically induced EMF. Before that, let us understand what is statically induced EMF and then move on to the dynamically induced EMF. So statically and dynamic induced EMF. So let me take that. Statically induced EMF. Okay, so see, you should understand EMF can be developed in a conductor. Okay, only two possibilities. That is, a conductor is stationary. Okay, conductor is stationary and the magnetic field moving. Okay, if the conductor is moving other way, that is first condition. Let me say this is first condition, this is second condition. If conductor is moving, then the magnetic field should be stationary. In both the case, the EMF is induced. So what we have to understand here is the EMF is induced, okay, when there is a relative motion between the conductor and the magnetic field. So, under statically induced EMF, we have self-induced again and mutually induced. Okay, we discuss about self-induced and mutually induced. So, when a conductor is stationary, as I said, let us take the first case. Okay, first case says the conductor is stationary and the magnetic field is moving. The EMF induced is called statically induced EMF. So this goes to case 1, first case. Okay, that is conductor being stationary and the field is moving. Then whatever EMF induced is called statically induced EMF. Now you can understand what is dynamically induced EMF then. So dynamically induced EMF is where the conductor is moving. So it's dynamic. Conductor is moving and the field is stationary. Then it is called dynamically induced EMF. So as I said, let us discuss on self-induced EMF and mutually induced EMF before going on to dynamically induced EMF. So as I said, statically induced, we have two types. We have two types. One is self-induced and second one is mutually induced. Let us take the first part now. Let us take the solenoid, as I said. Okay, it has number of turns here and this number of turns I'm giving it to some voltage. Okay, so as soon as I give the voltage, the current flows here. Okay, negative to positive. So the current flows here, I, and it comes back. So if I say the current flows here and come back, and suppose I say this is North Pole and South Pole, the lines or field lines would be in this direction. So let me mark it in a blue lines. So the magnetic field lines formed will be in this way. So the flow direction of the field will be in this direction, that is north to south pole. North to south pole. So as I said, self-induced EMF, if you observe here, when I pass a current in this solenoid, it produces a flux. That flux will link the coil, that is the coil wounded on the solenoid, and EMF is produced, okay, or induced, which is called self-induced. That is called self-induced. This is the case I'm talking, okay, self-induced. So we can write E is equal to, as I said, minus n d phi by dt in the previous video, which we explained about the induced EMF. Okay, since I'm talking about a coil, correct, coil wound here, since this is a coil, so instead of number of turns, I can use this as E is equal to minus L into di by dt. Why? Because flux is depending on current, correct? No, flux is proportional to the current. So when I apply a voltage, current flows here, and because of this current, flux is produced, and because of this flux linking the coil, the EMF is induced. So we can write E is equal to minus L into di by dt, where I replace phi by I because phi is proportional to I here. Okay, so this is about the self-induced. Then what is mutually induced here now? So mutually induced here, if you take two solenoid, okay, and I'm giving one of the coil the voltage and the other coil I'm just connecting the other coil to the galvanometer, okay, where I will show a galvanometer here. Now, as I said, when you apply the voltage, okay, when you apply the voltage, the current flows here, okay, and this current will produce a magnetic field here, okay, okay, and it will also produce here, if you look at this, so some of these fluxes will start linking here, okay, so when it start linking this coil, so EMF is induced here, and that EMF induced here is absorbed. EMF means voltage. So once EMF is induced in the coil, the current flows in the coil, and the galvanometer shows the deflection. So indication of the deflection in the galvanometer shows that an EMF is induced. That is why the current is flowing here. So we have again, because of that induced EMF and current flowing, flux is produced. That flux also starts linking to this now, this one, okay, so this coil, so it is mutual here. So we can say whenever the current in coil, if I say this is coil A and this is coil B, so we can say whenever the current in coil A changes, the flux linking with the coil B also changes. Correct, no? The amount of flux produced by this current changes. The flux linking this coil also changes. So, and an EMF known as mutually induced EMF. If you look at this solenoid doesn't have an electrical connection with this, correct? So, still you can see the deflection. That means without an electrical connection, you can still find an EMF getting induced in the next coil. So, this is called mutually induced EMF. That is because of the current changing in coil A. Okay, the flux changes, and that flux will not only link the coil A, it will also link the coil B. So the flux of coil A linking the coil B is called as mutually induced EMF. Okay, so the mutually induced EMF in coil B persist as long as the current in coil A is changing. So if you remove this voltage here, the current stops. There is no mutual induced EMF in this coil. So as long as your voltage is constant, the current is constant, flux is constant, the flux linking the coil B is also constant, correct? That is how it is possible. So if current A is constant, okay, though the flux is linking the coils, there is no change in the flux linkage, then the EMF induced is zero. So the magnitude of mutually induced EMF will depend on, again, the number of turns on this coil, okay, and the amount of flux linking this coil. So direction of the induced EMF is again given by the Faraday's laws of electromagnet. Direction of the induced EMF is given by Lenz's law. Suppose if I say M is the mutually induced EMF, which is depending on N2, that is the N2 turns of this coil B. If I say this is N1 turns, let me call this as N2 turns. So N2 into phi 1. Why I am taking phi 1? Because the flux linking this coil N2 is from this coil. That is phi 1 divided by, okay, I1. Because it is depending on the magnitude of the current also. So you can write N phi 1 is equal to M into I1. Similarly, I can write this, or minus n2 into phi 1 is equal to minus m into I1. So differentiating on both the side. So what we can get now, this equation, differentiating on both the side. So differentiating this equation on the both the side, okay, this equation I'm talking. So what you get, minus d by dt n2 phi 1 is equal to minus m into di1 by dt. Correct. Here m is constant. You should know the mutual induced EMF, we call it as m, denoted by m, which is constant here. But we know minus d by dt n2 phi 1 is equal to mutually induced EMF. Correct? No? That is mutually induced EMF. So we can write this one as EM, mutually induced EMF is denoted as E suffix M, is equal to minus M into di1 by dt. Okay, so this is how we can explain the self-induced EMF and mutually induced EMF. So let us now discuss on dynamically induced EMF. So as I said, dynamically, when a magnetic field is stationary, because I told you the condition here, so either the field should be stationary and the conductor rotating. So in this case, the conductor is rotating, so field is stationary, then the EMF induced is called dynamically induced EMF here. So I have shown here the conductor placed in between the field, and imagine it is rotating, then dynamically induced EMF is produced. So we can write mathematical equations for this as E is equal to flux cut, amount of flux cut divided by time. So this can also, how much amount flux cut, that is phi, we have written this equation in the earlier, B into L into dx by dt. So E can be written as E is equal to V into L dx by dt. So this can be written as BL into V. Why V? This is the velocity, dx by dt. Okay, dx by dt can be written as velocity. V is equal to dx differentiation of distance with respect to time. So this can be written as BLV volts. Okay, so this is how we normally discuss about the dynamically induced EMF. So in the next video, we'll discuss on what is self-inductance and mutual inductance, and then what is the coefficient of coupling, also in the next chapter. Thank you for watching this video.